Insights for your students.
Κλείσαμε το προηγούμενο. Νομίζω είμαστε έτοιμοι.
Excellent, please.
All right. Thank you, Mr. Vardis. And I would also like to thank Professor Mitrouli for giving me this opportunity to deepen my knowledge in numerical linear algebra. Now, our main problem for today is this least squares problem, and where we have a data matrix X with dimensions n by d plus 1. Now, in this problem, we have d plus 1 to be much larger than n, and that means that X is a high-dimensional matrix. While Y and X are given, we are now trying to find the regression parameter beta, and that's our goal. The epsilon represents a small noise that will allow us to observe how stable is the system regarding X's structure. Now, in order to do that and solve this problem, we will have to choose between two paths. The first one is a direct method. In solving directly, we will use the minimum norm solution, also known as the MNS. In this method, we will try to minimize this norm, y minus x beta. The second path we may follow is the regularization path. There are two ways of regularizing. The first one is Tikhonov, and the other is LPLQ. Now we have more parameters, and thus yielding more accurate results. However, in this way, we are solving a different problem, and that's important to know. So our main motivation is, do we really need regularization techniques or not? And that's exactly what is the objective of this research. At first, we studied the data matrix, X, and its properties. Now, we can analyze the data matrix and decide whether we really need regularization. Our first method of doing so is the minimum norm solution. Now, in this method, we are trying to minimize that norm, which we already have mentioned. Using several theorems and our knowledge from linear algebra, we can now conclude that this is the solution for our problem. This matrix is also called the pseudo-inverse matrix of X. Now, the second method is the Tikhonov regularization, also known as ridge regression. Here, we introduce parameter lambda, and now we are able to find a more accurate solution. Below, we see this identity, which is the identity of the solution for the Tikhonov case. And we can now find the optimal lambda value using the discrepancy principle. However, the third and most complicated method is the LPLQ regularization. In this method, we have now not one, not two, but three parameters, mi, p, and q. It is very important that we find their optimal values, And we now understand why it is very important to have this in mind that that finding parameters can be very expensive, and avoiding regularization can save us time and memory. Now, the next step is to construct the design matrix. Our first method would be the column correlated covariates, also known as CCC. We let He be the column, the ith column. Hi is the ith column of the design matrix, and we will have two variables. The first one is R and sigma, the second one. Sigma is, of course, the variance of um, uh, our normal distribution, and R is the correlation coefficient. It's also called as the Pearson R. That means that we measure the linear correlation between the columns of X. Now, this identity will be true for the desired R and the columns of the data matrix. Here we have the second way of constructing the design matrix. This is the element correlated covariates, also known as ECC. We can define the matrix sigma, which is a square matrix, and its elements are defined by this formula. It's pretty obvious now to observe that every element of the diagonal of sigma is exactly 1, so sigma, the variance, is 1. Now we will calculate all the elements using the normal distribution with a variance of the sigma matrix and a mean of 0, as always. This is also depicted in the following algorithm, which uses the exact aforementioned commands. Now let's head on to the numerical implementation. It's time for our simulation, or we need to, at first we need to assess which method is best. We can do that by applying a simple error. We find the relative error, the relative square error of each simulation, and then we are going to find its mean value. That way, we can call it relative mean square error. That's the acronym we are seeing by our screen. And this is the algorithm we use for our simulation. At first, we have as our input the data matrix X, and now we generate the veta. This is a vector, a random vector from a normal distribution. This is the desired vector, and that's our goal should be to find it. Now we calculate the vector Y, and our next step is to do many times this loop. We add noise to the Y and then find the three different solutions, one for each method. The goal of the algorithm is to return the relative mean square error. Note that our whole simulation has been done using the Julia programming language. Now, the results of the simulation were very interesting. In using the CCC method, we can observe that if we test for R equals 0.5, which means that the X is lowly correlated, not highly, and we can see that the MNS works sufficiently. So regularization seems unnecessary. The Tikhonov and the LPLQ methods are of higher complexity. So even if we use either of them, we will waste time and memory, which can be valuable. However, as the data becomes more correlated, the Tikhonov and the LPLQ methods are needed. For smaller R, for example, 0.9, we can see that MNS is no longer accurate. The errors of MNS are greater than expected, and thus we will have to use regularization techniques. The Tikhonov is a very sufficient one, and we can also use the LPLQ method. The latter depends on more parameters, and we can find the optimal value or the optimal solution for our problem. Now we follow the same procedure for the same problem, and we expand the design matrix with dimensions to 50 to 101. Note that the previous dimensions were 5 by 21. Now, we can see that the results are very similar, and the aforementioned points are being confirmed. In case R equals 0.999, that is a very high correlation coefficient, the LPLQ method is the most accurate one, especially when compared with the MNS. Now, we will try to simulate our problem for the ECC method. We can observe that because of our definition, the variance sigma tetragonal is always 1, so we don't need to mention that. As we can see, the results are also very similar. That is confirmed in the next matrices too. The MNS is very close in these stages. However, in 0.999, the MNS is no longer sufficient, so we are going to have to use regularization techniques. However, when we get past the 1000 barrier, MNS seems no longer so weak in the highly correlated matrix. As we can see, this is a 50 by 1001 X matrix, so the MNS seems to work sufficiently, and regularization is no longer recommended. That is also confirmed in bigger dimensions, 100 by 2001. So our conclusions would be that the regularization should be applied only if X is highly correlated. The MNS can yield satisfactory results in case the X is not highly correlated. And when the circumstances allow it, we should avoid regularization and thus save time and memory with faster and more efficient computations. That can be summarized and visualized by the following diagram. If we have highly correlated results, approximately 1, we will use regularization techniques. However, with not highly correlated results, we may use MNS. Here, our presentation is over, and any questions would be welcome.
Thank you very much. Any questions, please? From online.
And you just tell us, Nico, finally, if we can learn from the data, if we can apply regularization or not. Since it's an expensive procedure, the whole regularization, and whatever we are hearing about, most of them apply regularization without really try if it is needed or not. So can we be guided from the data if it is needed to be applied?
Exactly.
What was your final finding?
Yes, thank you for your question. And exactly that's what our goal is, to learn from the data, to see the properties of our matrix, our design matrix X, and to see if to conclude if regularization is needed at all times or at specific times under some certain circumstances we have to find. Yes, that's our goal, learning from the data.
Please,
You try
Professor.
to apply the LKQ method for different pairs of parameters.
Thank you for your question. Now, of course, we tried, and in the previous slides, you may see that we have, of course, written down every P and Q that yields the best results, and that's exactly what we were trying to do. We may see that sometimes for P equals Q equals 2, that the problem reduces to Tikhonov regularization, and that happens. That doesn't happen. However, it can be close.
Any more questions? Thank you very much. Next presentation is by Philippos Patalos.